upload them, but you also have access to Brightspace. I don't know if you saw whether you want to create your own folder, Dave, on Brightspace and upload. I mean, or you just send them to me and I'll drop them in to
All right.
separate folders. I've been creating a subject specific folder for on Brightspace as well, for them to usually go looking as so.
Cool. All right.
All right, then.
Let the fun begin.
Let the fun begin.
Or end, depending on your perspective.
I
All right.
guess it depends which subject you're going to do first, right? I got a C in material science. I hated that stuff or whatever. I know, strength, but anyway.
Yeah. All right. So I'm hoping everybody can see my screen here that is largely blank. This is where we'll be conducting our review. And as with the previous review I had done with you, what I will be doing is working my way through the FE handbook and just reminding you of these concepts that we've seen in theory of structures and what we're doing with them and remind you of how to use them. And at that point, I'll sort of check in on what do you need specific work on, what should we actively focus on for the remainder of our time. I would also like to point out that here I've been invited not only to review structures, but also to review materials. And materials, we're essentially looking at concrete design, concrete mix design for the most part. There are no tables or any information provided about this. So basically, you remember that your water to cement ratio drives your quality and strength. And that generally a high water to cement ratio gives you a lower strength, and that generally a low water to cement ratio leads to a higher strength. And the other aspect of materials is just general material behavior. There could be some other more explicit, more specific questions, but I have a hard time believing that in the scope of the FE, they're really looking into excruciating detail on materials. So from the materials end of things, there's basically your review. My understanding, again, from students who have recently taken the FE, that there's not a lot of super detailed stuff about that. Now, on the structure side, however, there's a lot of potential detail, and it's all, again, coming from here. So I'm going to just start with, so this is the civil engineering structural analysis part. This is where it starts. It's right after the geotech, so I don't remember any of the stuff on this previous page. Here's the structural analysis part. So I'm going to start copying over a couple things at a time here. This first segment, this is all about our influence lines, which of course, influence lines being everybody's favorite topic from structural analysis. Everybody remembers how to do them extremely well. Influence lines are the reverse of our shear and moment diagrams. Here it's showing the variation of an effect. We talked about reactions and shear and moment, and we did forces and truss members as well. So we're looking at moving this unit load across the structure and finding out the structural response at some position with respect to this moving load. And that allows us to maximize the effect. So our influence lines, the basic concept is there. I can go through that a little bit later if that's something that you decide you want me to review. Influence lines are very much related to this moving set of concentrated loads. So here, we've got these loads P1, P2, up to Pn. So there are these n moving loads. And this is all about determining the magnitude and position of the absolute maximum moment produced in the beam. So we have a simply supported beam, and here what you have to do is position the resultant R equidistant. The center line of the beam is equidistant from the resultant R and one of the adjacent forces. So when you're determining your, based on your loads P1, P2, Pn, you find the resultant force and its location, and now we would check the position of this moving load set with respect to the center line of the beam, such that the center line is equidistant from R and P2, and the alternative position is where the center line is equidistant from P1 and R. So just those two positions. And then what you would be looking at here is you would find your moment here for this particular loading. The other loading is your center line equidistant from P1 and R. And so for that condition, the maximum moment would occur underneath load P1. And those are purely these static checks. I mean, it's literally just going through and finding that resultant force, putting it on the beam, and checking statics for the internal moment at each of these locations. All right. So again, we can circle back later and talk about specifics of such and such topic, whatever. But what I want to get to next is the next subject, the next content here in the handout. Now, the next content is actually split up into multiple places. So I'm going to put a little divider here. So that first set of material is related to influence lines. Our second set of material is related to statically indeterminate structures. Because, of course, in statics, you learned how to manage statically determinate structures. So we've got this beam stiffness and moment carryover. Then we skip a little bit. Truss deflection by unit load method, that's different. Frame deflection by unit load method, that's different. Here we have the force method of analysis. This is part of indeterminate structures, but I'm going to come back to that because I want to jump to these member fixed end moments. So these pieces are used for the moment distribution method. And again, they're separated from one another in the actual handbook, but that's okay. They're not overwhelmingly challenging to find. So we need these. And in terms of the other content relating to statically indeterminate structures, we've got this concept here. Let me actually zoom out more. There we go. So statically indeterminate structures can be solved by the moment distribution method or by the force method. And there are undoubtedly situations where one method is better than the other, and that's all great. The force method is particularly useful when you have just one degree of indeterminacy. So when I look at this structure, so they actually provide an example here to demonstrate, actually two different examples to demonstrate this concept. So let's separate those out here. So here's example 1, and here's example 2. So in the first example, our beam has supports at A, B, and C. A is a pin, B is a roller, and C is a roller. We have 4 reactions. And so what we've done is we've identified a redundant reaction. And that redundant reaction is then removed. So here, this loading, we've removed our redundant. And now we put our force from the redundant reaction. And we note its effect. So essentially what we're doing here is getting compatibility, where the real displacement at point B is 0 because of the support. And so that is equal to this vertical deflection from the actual loading plus this vertical deflection from the redundant reaction. And in this case, the convention that they used was positive upward. So that's why delta BB, capital delta BB is negative, whereas lowercase delta BB is positive. So we add those two things together, you'll get a positive value for BY. The second problem is dealing with the same idea here. We have 3 reactions at A, we have 1 reaction at B, and again, that reaction at B is redundant or selected as the redundant reaction. Your structure is perfectly stable without it, and in fact, it is solvable without it. So we remove the redundant reaction, and we return its force quantity, and again, we're finding those deflections, and again, we're looking at compatibility of the deflections with respect to the original problem. Again, at B, no displacement, which is equal to this negative displacement from the actual load after removing the support, and this positive displacement from the redundant reaction force applied to the location of the redundant. So that's our force method in a nutshell, conveniently presented on a single page of our handout. And again, these aspects for the moment distribution method are provided on 2 very different pages for your sheer inconvenience. So these are the topics relating to statically indeterminate structures. I am fully expecting at this point that I'll be circling back to present a little bit of the moment distribution method, just to go through that as an example to help set the stage for how to do that. All right, so the next content. So going back to the first page here, we have truss deflection by the unit load method. Blow this up a little bit. We're now getting into virtual work. Which is your entire semester right now, right? Yeah, I'm not proud of that. All right, and both of these methods here where we're looking at trusses and again where we're looking at our frames, these are both variations of virtual work. So there's trusses with this equation here, and we also have frames or beams with this deflection equation here. Fundamentally, these work the same way. You can see, of course, the truss one has, it's just algebraic addition of these discrete values, whereas the beams, it's integration, which means, of course, that everybody's favorite is the beam version. So there's virtual work. Now you know why I spent so much time trying to drill that in on you, and to no great avail in some cases. We've got, again, the force method. We already briefly talked about that. We've got the member fixed end moments. We already brought that up. The last distinct topic, because then we go into structural design, which I believe Dr. Patnaik either will review or has reviewed for you. The last topic here is stability and indeterminacy. And it uses a set of equations we're familiar with and a set of equations we're not familiar with necessarily. So for our plane truss, these equations are just like the ones we used from 4300 306. I believe we used B plus R instead of M plus R, but it's the number of members, the number of reaction forces, and that has to be less than, it has to be equal to the number of, twice the number of joints to get you a stable and statically determinate truss. And that's because at each joint, when you draw a free body diagram, you have two equations of equilibrium. For your plane frame, it's a little messier. These equations are different from what we talked about in class, although I have been trying to, let me erase that. I have been trying to bring these equations into class to some extent as well. So sometimes I get around to that and sometimes I don't. So this is a little different from class. But fundamentally, it's the exact same thing. It's just a little bit of a different presentation compared to what we're potentially accustomed to. And the basic idea here is that you're still doing some fundamental counting, and that count is going to set your stability, I'm sorry, not your stability, your determinacy, and potentially stability. But there are still some additional considerations for stability. Oops, that's not what I wanted to do. Supposed to be the orange. This is the one I want. All right. This statement is also important. So first, I want to just show the plane frame classification, and then we'll talk about this yellow highlighted statement. So I'll actually erase my little line here. So our frame classification. So let's look at, say, a cantilever beam. So there's our cantilever beam. And we need to count the number of members, the number of reactions, the number of joints, and the number of condition equations. Okay, so let's deal with each of these. I have one member. So M is equal to 1, right? That cantilever beam is a single component. I have reactions. 1, 2, 3 reactions at my fixed support. So R is equal to 3. I have a number of joints. There's 1 joint. There are 2 joints. So just like your forearm you have 2 joints. You have your wrist and your elbow, and your forearm connects those two. This beam connects its beginning node or joint and its end joint. So N is equal to 2. And so what we're looking to do here is compare 3m plus r versus 3j plus c. Now here, c is equal to 0. Because we don't know any specific values anywhere in terms of moments and forces. So c is 0 here. And so now I look at 3m plus r and compare it to 3j plus c. So 3m is 3 plus our reactions, which are 3, and we're comparing that against 3j, where I apparently wrote n instead of j, so that's good. It's good, keeping myself on my toes. 3j is 6, plus c is 0, and 3 plus 3 is equal to 6. This is statically determinate. And hopefully you did not need me to back this up with math to verify that a cantilever beam is indeed statically determinate. So let's change this slightly. Let's make this a little more fun. Fun being a relative term here. Let's take this cantilever beam, which we know is statically determinate. Let's add a support. Let's make it a propped cantilever. But now I'm going to make it a propped cantilever with an overhang. All right, so imagine, if you will, that your hip represents the fixed support, your knee is here resting on something, and your leg is just sticking out from there. So there we go. And the reason that I want you to think about it that way is because now we have 2 members. So here is member 1, and here is member 2, your upper leg and lower leg there. M is equal to 2. We need our reactions. Well, I've got 1, 2, 3, 4 reactions. We need our joints. I've got 1, 2, 3 joints. And again, I don't know any of these internal forces. All right, so again, 3m plus r is compared versus 3j plus c. 3m is 6, r is 4, 3j is 9, and c is 0. 6 plus 4 is greater than 9 plus 0. So this is indeterminate, because we're in the greater than territory. And just to, of course you realize this because we have 1 support reaction that we don't need. It's extra. The last aspect here, just to bring this back in and show you what C does. Take that same propped cantilever, but now I'm going to put a hinge on it. And we're going to look at this again. We're going to go M, R, J, C. It's going to be fun. So here's M. We have, sorry, supposed to take my evening pills. The members 1, 2, and 3. M is 3. Reactions, I've got 1, 2, 3, 4. R is 4. We've got joints. 1, 2, 3, 4. And now I've got a hinge. I know that the moment is equal to 0 at the hinge. C is 1. There is one internal force quantity that I know about this problem. 3m plus r versus 3j plus c. All right, so we're at 3m. 9 plus our number of reactions is 4. 3j is 12. Plus our number of condition equations, 1. 13 is equal to 13. This is a determinate structure because the left side and right side are equal to one another. So it's all about counting. And this works with frames, so I could have, instead of aligning this all in one linear segment, I could have done it in multiple pieces. It doesn't matter. Just remember that you only need to change the member if you have a point of interest on it. So here, when we have the cantilever with a support at mid-span, that support becomes a node, and it separates out the member. I find that much more helpful to think in terms of that. The last thing I want to go through here real quick, arguably, is that stability requires an appropriate arrangement of members and reaction components. So the appropriate arrangement of members, you should first think in terms of truss members for that. So our stability So first of all, if you don't have enough reactions, you have an unstable structure. So for instance, when I have a beam supported by 2 rollers, I have 2 reactions. I need 3 for it to be stable, right? M is equal to 1, R is equal to 2, J is equal to 2. We have 5 on the left side, 6 on the right side. This is unstable. That's what the math tells us. However, if I add a third reaction that's also from a roller, here my reactions are all parallel. So all reactions are parallel. This is unstable. Right? This goes to the idea of I can go out and find my car and put it in neutral and release the parking brake and just give it a shove, and it just goes. That's not what you want a structure to do. So if all the reactions are parallel, this is unstable. The other condition that leads to instability, the other common condition for a beam that would lead to instability, and it's also true of a truss. If all reactions are parallel for a beam or a truss, if this other condition is true for a beam or a truss, it's also problematic. So in this condition, I've got my reaction forces here and my reaction force here, and here all reaction forces are concurrent. The line of action of each of these forces, those lines of action all intersect at this point, which means any kind of force applied to this structure that would cause a moment about this point cannot be resisted. This is unstable. And the final instability condition is very truss specific. Remember that trusses are built on triangles. We can have a bunch of truss elements connected in a square instead of triangles. And the problem with this is if I apply any lateral force to it, I have a collapse mechanism. Right? These are pinned joints. So this truss wants to deform like this, and then it wants to deform like this, and then it just wants to deform like this. And the poor souls inside that truss have been crushed, like my dreams. I don't dream about people being crushed. It's my dreams being crushed. Anyway, so those are the fundamental concerns that are addressed by this little yellow highlighted statement, an appropriate arrangement of members and reaction components. Circle this here because that's related to that highlighted statement. So at this point, what I'm expecting is that we're going to sort of look at some examples of how to manage these different topics. Obviously, some of them I went through at least to some extent. I would like to think that this stability, determinacy, classification of structures, I would like to think this is relatively straightforward at this point, or at least in terms of the likelihood you'd get it and your relative comfort with that topic. The virtual work stuff I expect is potentially a little bit hazy in the rear view mirror. Particularly, I know a lot of you took theory of structures a year and a half ago. So I can't imagine you're remembering this with great fondness or with great clarity. So I'm expecting to go through these two topics to some extent. The force method, genuinely not terrible, honestly, believe it or not. Moment distribution isn't as bad as it seems either, but it's a little more complicated, I'd say. And influence lines, again, I have a hard time believing anybody remembers them particularly well, but I'm willing to go through anything that anybody feels would be useful to look at. Does anybody have any explicit questions or concerns, or should I just start doing what I want to do? I'm looking for guidance here.
I'm good with you starting just doing what you gotta do.
All right, I can do that. I'm just looking for some specific information in the handbook. And it must be in the mechanics of materials stuff. There we go. So one thing that I want to explicitly point out, particularly here when we have the force method. The force method, we're seeing that they have just pulled up an equation for the displacement at midspan under this load. They've pulled up an equation for displacement under this load as well. Those equations exist in the handbook. They're not just making them up. And here in the handbook, in the mechanics of materials section, way at the end of it, we get to simply supported beam slopes and deflections, and cantilevered beam slopes and deflections. So any of the loadings shown in this document could be on your exam in terms of using the force method to solve them. And then there's piping segment, and that's just crazy talk. So I'm going to copy this stuff in as well into my little document, because that's useful. And I'm keeping that mechanics of materials header on them to remind you that that's where it came from. All right. So why don't we just talk about the force method here while we're looking at something directly related to those displacements. So our force method is all about dealing with a single degree of indeterminacy. So I could take, for instance, this propped cantilever and say this is a structure with a single degree of indeterminacy. We'll look at the relative validity of doing that. Yes, we can absolutely do that. So let's take a look at this thing and try to understand how we can deal with that with the force method. So I'm going to go ahead and say I'm going to take a propped cantilever, force method here. And so I have a propped cantilever. And it is subjected to just a uniformly distributed load along its length. Actually, you know what? Let's make it a little more fun than that. Let's do a triangular distributed load. And let's say that it's loaded to 10 kilonewtons per meter at this end, and the beam has a total length of 10 meters. So there we go. There is our structure. And this beam has some elastic modulus E and some moment of inertia I. Those are constant. They might be given values, whatever, but we have them. And so what we need to do is look at this structure and say, what reactions do we have? So let's draw this as a free body diagram. And what I like to do with my free body diagrams is just cheat and use my initial sketch. And so I will say that I have reactions AY, AX, and AM. And I have reaction BY. So I have 4 reaction forces. And I know that since I only have this one continuous beam, basically, I need only 3 reactions. I can only solve 3 because I can sum forces in the X, Y, some forces in the X and Y directions and some moments, which is actually about the Z axis. So I can only solve 3 unknowns. There's 4 here. The only ones that are really critically necessary, AX is the only critically necessary reaction force. I cannot choose that as a redundant reaction because without that, I have a car. This thing can move left and right to its heart content. So one of the other reactions has to be the redundant reaction. And really what you want to try to do is get to the condition where you either have a simply supported beam or a cantilever beam. And so I should select By as my redundant reaction. And just to I guess illustrate a contrary situation, if I took my propped cantilever and had the roller support at this end, I could alternatively select my moment as my redundant reaction. Because here, if I select the moment as the redundant reaction, I'm left with a simply supported beam. Just as an example of another way to do this. But here we're going to say By is my redundant reaction. And so what I am going to do is I'm going to say that this condition is going to be equal to the summation of two statically determinate problems. So here I have points A, B, and C, plus this alternative beam with still points A, B, and C. And all of these dimensions are still the same. 5 meters from A to B, 5 meters from B to C, and here as well. And so what I'm doing on the first problem is taking my original loading. So here is my triangular distributed load. Acting on the beam, I have reaction forces. I have AY1, AX1, and AM1. And you'll note that I'm drawing them with the exact same assumptions of direction that I did in the original, in the indeterminate problem. So AY is still upward, AX is still to the right, AM is still clockwise. But now I've given them, first of all, a different color, but also a subscript of 1 to fill this out. My other problem, I bring back my redundant reaction force. So we're not bringing the support back, we're just bringing in that force. And again, that leads me to get some reactions. AY2, AX2, and AM2. So we can go through and say, I want to actually treat this, the way we did this in class, is I said, forget about this stuff on the right-hand side. I don't want this in terms of By. I want this in terms of a unit force, which means these reactions are lowercase AY1, AY2, lowercase AX2, lowercase AM2. And what we're going to do is multiply this entire problem times By. This is how we did it in class. It's fundamentally the exact same thing, right? So what I'm saying here is that AY2, for instance, is lowercase AY2 times By. That's it. Nice and easy. So statically, we're saying that AM is AM1. Let me just write this. So from statics, we have AM, right? That clockwise reaction is equal to AM1, which is also a clockwise reaction, plus lowercase AM2 times BY. Again, AM2 is clockwise. So that's why I'm consistent with orientation of all of these. My reaction moment is clockwise in each of these figures. My reaction vertical force is upward in each of these figures. The same with the horizontal force being to the right, just being consistent. And so this statics condition is true of every quantity. So we're looking at the force at B. I have By in the original, in the indeterminate problem. Well, that's equal to 0 from this problem, right? There's no force at B here, plus 1 times By. Again, we're looking at these as both being upward. So our statics is satisfied from the indeterminate problem and these two combined determinate problems. Where things fall apart is the deformed shapes, right? The deformation of this looks something like that. The deformation of our second problem looks something like this. And the problem that we have is the deformation here is actually 0. So what we need to do is determine the magnitude here, which we will call delta B, capital delta B. And here in class, we would have treated this as FBB. And we would have said that lowercase delta b, which is positive upward, is equal to FBB, which is also positive upward, times BY. Again, you can just put BY there and calculate lowercase delta b, whatever works for you. And here, delta b, capital delta B, is negative because it's positive upward. We want to be consistent. Our deformation is positive upward. So what I need to do now is go into the tables and say, what is the displacement at B? Well, here, that tells me where point B is. And here, if A is equal to 0.5 L, I have my loading at B. And so what we're able to see here is that your elastic curve will tell you your displacement for x equal to A. And here it will tell you your displacement for x is equal to 0.5 L. So when A is equal to L over 2, we're going to find FBB. Now, please note this direction. They're showing you all these quantities downward, which is why this thing is negative. So you have to be mindful of that because the force I drew here is pointing upward, so I would need to negate the negative sign. Whereas here, this equation is negative because this is downward, and that's true. So be mindful of your signs here. But that's literally all you have to do. So we're finding delta B is a calculated quantity. It's some function of that stiffness, the beam stiffness EI. right? And there's the EI in the denominator of both of these equations. We're going to find that delta B, or FBB, is a function of our loading. And so this delta B is a function of By as well as your stiffness EI. And your displacement at B is equal to 0. Again, there's a support there. And that is equal to delta B plus lowercase delta B. So obviously I'm skipping the part where I would plug into those equations because of course the loading I gave is not conducive to quick solving, but hopefully this is sufficiently thorough to demonstrate the concepts. Any questions, comments, concerns about the force method? All right, we've got the force method down. So let's look real quick at the other indeterminacy, the moment distribution method. And moment distribution method is definitely more complicated. There's a process that you have to go through to find this stuff, but it's genuinely not too bad. So what you would do is we would start with a statically indeterminate structure. Oh, bugger, what color was that? Moment distribution method, I did orange. Oh, well. Oh, well. We'll do it this way. Now, typically what you'd want is, for the moment distribution method, you want a much greater degree of indeterminacy based on forces. So with the moment distribution method, we'd want to look at something that is, say, a situation like this. Two fixed ends, a roller in the middle. This is indeterminate to the fourth degree by forces. And then we can throw some loading on here and say, oh, we've got this uniformly distributed load here, and we've got this concentrated force at mid-span here, and so this is W, and this is P, and that's great, and we've got all these reaction forces. What on earth do we do? Well, what we're able to do with the moment distribution method is pull out these segments. So if I say this segment here, trying to make that solid, there we go. If I pull that out, and let's just say we have points A, B, and C, then this is ends A and B of that segment. Well, I've got a bunch of internal forces here. I've got shear, normal force, so this is to the left of point B. Right, so here I have BL and BR. So this is just to the left of B. So I have the shear just to the left of B, and the normal force just to the left of B. That's great. But I also have moments. And this moment distribution method, I'm going to say I have MAB and MBA. And I know, first of all, that MBA is drawn in what is traditionally a negative moment direction, but this moment distribution method, as we learned it, is based on clockwise positive. So we're we're going to take this and we're going to go through and we're going to say, I can solve all this based on this process where what I need to do here is determine these various stiffness factors for each part of the structure, for each of these segments. So let me pull up that handy dandy section of the book. So here, this beam stiffness and moment carryover, this is what we're using. And I'll just reproduce it again, because I can, that's why. And so we have this stiffness for EI over L. Now, this is actually based on a fixed end beam. I know what's shown up there is a pin on one end and a fixed end on the other, but this is true for this fixed condition. And so what we're saying is that here at the absolute left end of the beam, I've got two sides to this. I've got the wall, and I've got span AB. And the wall has infinite stiffness. And span AB has stiffness of 4 EI over the length of AB. And so what we're trying to get to is the relative stiffness of AB here. So our total stiffness at A, I put those two together and I get infinity, right? Infinity plus something is still infinity. So our relative stiffness again, thinking about these two sides, we've got the wall and AB. The wall has a relative stiffness of 1, AB has a relative stiffness of 0. And then we look at joint B. And again, we look at this and we say, okay, at joint B, I've got AB and BC. Well, AB has a stiffness of 4 EI over the length of span AB. BC has a stiffness of 4 EI divided by the length of span BC. At C, I can do this exact same thing still. I have BC and I have the wall. At BC, I have stiffness 4 EI over the length of BC. At the wall, I have infinity. Relative stiffnesses are going to be 0 and 1. And AB and BC are dependent on a whole bunch of things. Let's just say, for argument's sake, it's half and half. What it should be is, so these relative stiffnesses are our distribution factors. And each distribution factor is equal to K divided by the total K at the joint. And so here I'm just arbitrarily deciding that AB and BC have equal stiffness because they have equal lengths, whatever. And so the process here, what we're going to do is we're going to, now that we've established our distribution factors, we need to consider what our fixed end moments are. That's the next step in this process. So I'm going to carry these lines down. I'm not going to go through the whole thing. I'm just going to get the ball rolling here to demonstrate how this works. And your fixed end moments are, again, based on information provided in our handout, in our FE handbook. It's in here. Just got to keep scrolling. There it is. Our fixed end moments for exactly these two loading conditions. And so when we're looking at these, what we should be remembering is that our convention is clockwise positive. So for this lower condition here, FEM-AB actually needs to be made a negative quantity, right? What they're showing is that that fixed end moment is counterclockwise, but we're working with clockwise positive. FEM-BA is positive. FEM-AB is negative, and FEM-BA is positive. So here I have negative WL squared over 12, or I have positive WL squared over 12. And so what we do is, based on our loading, we actually compute these. So here we're saying that our fixed end moments are in, say, kip feet. And so for this left span, span AB, I'm using this condition. So this is span AB. And I know I'm going to have two equal and opposite values. So let's say I have negative 100 kip feet and positive 100 kip feet. Just making up numbers to get the ball rolling here. Great. And now for the right-hand span, span BC. We have this concentrated force. And I'm going to get two different values. Or maybe the load is at mid-span and I'm going to get the same value. Whatever. So let's say fixed end moment AB is negative 50 kip feet. And BA is positive 30 kip feet. Whatever. So our next step now, so this is all of the fixed end moments throughout the structure. Our next step is to apply equilibrium. Let's equilibrate. And so when we look at this, we see, okay, I have a fixed end at A and a fixed end at C. I'm already set. Those fixed ends can take whatever we try to throw at them. But here at B, I have positive 100 and negative 50. So to equilibrate that, I have to add in another negative 50, which has to be distributed based on our distribution factors. So our distribution factor is 0.5. So 0.5 times negative 50 is negative 25. 0.5 times negative 50 is negative 25. So we've accounted now for this negative 50, and we've distributed it to the two beams that frame into that joint. But now I have a carryover. The moment over 2 is carried over. So our carryover here, we're going to carry half of the negative 25 over from BC, from point B to point C. We're going to do it from point B to point A. And of course, the zeros don't need to be carried over at all. They're just zero. Doesn't matter. So now what we should do is check equilibrium. So at the left end, at the wall at A, I have negative 100, minus 12.5, negative 112.5. This is in hip feet again. Here at the left-hand side of joint B, I have positive 100, minus 25, negative 75. Nope, that's positive 75. Wow. Mental math has failed me. The right-hand side of joint B, negative 50, minus 25, negative 75. Hey, the joint is in equilibrium now. It's subjected to a total moment of 0. That's what we want. And here on the right-hand side, positive 30 minus 12.5 is positive 17.5 kip feet. We've now completed this. And so when I look now, we're done because all joints are in equilibrium. So I can now draw a free body diagram of span AB, which is subjected to this uniformly distributed load, and I have end moments of negative 112.5 kip feet on the left-hand side and positive 75 kip feet on the right-hand side, both drawn clockwise positive. I also have the shear at A and the axial force at A, the shear at B on the left-hand side, and the axial force at B on the left-hand side. I can do the same with span BC. And our moments here are negative 75 kip feet on the left end and positive 17.5 kip feet on the right end. And I've got my concentrated force, wherever that was. And now, if we wanted to start actually solving reactions, which is extra time, this is a lot of time that you would have to spend on a single problem, so I don't anticipate it going into this grade of detail, but if you draw a free body diagram of joint B, you're actually able to solve for this reaction. So here's my reaction BY, and I have my internal shears VBR and VBL. I have my normal forces NBL, NBR, and I have my moments which, now that I'm drawing the joint, I should be showing my moments counterclockwise. And you see from moment equilibrium, that's how we're getting this condition where we have equilibrium at the joint. And because of that, we're able to go back and from the beam segments solve these shears, from the shears solve for the reaction force from equilibrium here at B. So that is the 15-minute version or 20-minute version of our moment distribution method. So we've done the force method, we've done the moment distribution method. Hopefully they're at least a little more approachable for you as you look to start practicing for the exam. Neither one is terrible to use, I promise. They just seem that way. So we've got influence lines, and again, from my perspective, the influence lines, predominantly you'd be looking at finding this max moment given a moving load. I can't imagine they're asking you to do too much of true influence line, but I'll be happy to do one of those real quick, and then just review the concepts of the virtual work method, which isn't too bad when you break it down. All right. Yeah, my 90 minutes here are chock full of just joy. So, influence lines. And I'm going to do something just really, really simple. I'm just going to look at a simply supported beam where I have points A, B, and C, where B is just a point at some position on the beam. And I want to draw influence lines for the reaction at A, so RAY, the reaction at C, for the shear at B, and the moment at B. And so I want to just go through the process of doing these things. So first things first, we need free body diagrams. And we need free body diagrams that show the various unknowns. So I have a free body diagram right here that shows, oh, may as well just go back to my old notation, AY, CY. I have a free body diagram right here that shows AY and CY. It's not very useful because it doesn't have a force on it. So let's put that force on it. And for our influence lines, we use a unit virtual force at some arbitrary position X. And here I've defined X as starting at the left end, so great, that's fine. And we'll say that this entire thing has some length, and furthermore, we'll say that I have length AB and length BC here. So X ranges from 0 to L, great, fine. From this free body diagram, I can solve for equations that define AY and CY. So for instance, if I were to sum the moments about point A, well, I know that I have to have equilibrium. I will assume clockwise is positive because why not? And so I have this force, this unit force, times its moment arm, X, minus my reaction CY times its moment arm, L. And so I can solve, and algebraically I will find that CY is equal to positive X over L. And so what I can do with that is make a plot of CY versus X, where X ranges from 0 to L, and CY will range from 0 when X is equal to 0, right? X equals 0, 0 over L is 0, to X equals L. This is a linear function, so I only need 2 points. When X is equal to L, C is equal to 1. So there's my influence line for CY. And now that I have that, I could even go one step further and say, let's sum the forces in the y direction. I'll assume downward is positive. That must equal 0. So I have negative AY plus 1 minus CY. And so AY is equal to 1 minus CY. Cy is x over L. So Ay is 1 minus x over L. And so if I were to plot Ay's function here, well, when I plug in x equal to 0, Ay is equal to 1. And when I plug in x equal to L, Ay is equal to 0. And I just connect the dots. It's a linear function. So there we go. Influence lines for these reaction forces. That's great. If I want to do this for shear and moment, I need to put together free body diagrams that show those shear and moment forces, those internal forces. And so I'm going to draw a free body diagram from A to B. I'm going to draw a free body diagram from B to C. I've got my reactions. Ay equal to 1 minus x over L. Cy equal to x over L. And now I have the internal quantities, V sub B, always drawn with the traditional positive sign convention. I've got my moment, M sub B, and I'm going to forget about horizontal forces. They're not relevant here. So the question becomes, where do I put the force? And the answer is, well, we put it everywhere along the beam. So I get to copy and paste because we're going to look at two conditions. We're going to look at case 1 where 0 is less than or equal to x is less than or equal to LAB. And we're going to look at case 2 where LAB is less than or equal to x is less than or equal to L. So in case 1, here's my force. Here's my distance x. Again, it's a unit force. And conveniently, I can solve for VB readily. Right? Vertical equilibrium. I can solve for MB is equal to x over L times LBC. Right? It's just from equilibrium. So this is sum of the forces in the y direction. This is sum of the moments about point B equal to 0. Great. Case 2, well, what I'm doing is I'm going to put my unit force over here. Some distance x from the left end. And now here in case 2, well, I would want to use this free body diagram, and I can solve for VB and MB readily here. So this way you can draw your shear and moment influence lines, and your diagrams for these I would look at VB, which is unitless, and VB is going to look something like this. MB, which has units of length, right? Our force quantities are unitless. Our moments would be unitless times length because it's force times distance. And our MB would look something like this when you actually work out these various functions. So that's the process of generating influence lines. Not too bad, right? It's just a matter of considering the different potential locations of your force. You have to break up your free body diagrams so that you're showing the unknown force quantity. If there are any hinges in a structure, you always have to break the structure at hinges, which means there are potentially more free body diagrams that your force can land on, which means maybe there are more than two cases. Maybe there's 3 or 4 or whatever. But if you have a structure with no hinges, this isn't so bad. So that's the story of influence lines. And with my 5 remaining minutes that I'm probably going to go over a little bit, just to make sure to be thorough, not as punishment for anything, though it does seem that way, I'm sure. Virtual work. What a topic to have 5 minutes for. Virtual work is all about order of operations. The idea here is that what we're trying to do is find deflections under a particular loading condition. And we can do that for a truss, and we can do that for a frame. And so the idea here is, if I have a truss, let's just draw a nice simple truss with whatever support conditions and whatever load conditions. Okay, so this is our loading condition on this truss, and we have joints A, B, C, D, E, and F. And what we're asked to do here is find your vertical displacement of joint C. And it really doesn't matter which joint you're asked for. What matters here is that we're noting the direction and the joint. And so what you're going to imagine in your mind, I mean, you're not really going to imagine this, but this is what we're actually doing here, is we're taking our truss, and before we apply that real load to it, we're going to apply a virtual load to it. So we have our real load, and we also have our virtual load. And our virtual load is a vertical load at joint C. And so you have a choice to make. Will it act up or down? It doesn't matter. So I'm going to put my virtual load upward. It's an arbitrary choice. So here the direction is arbitrary. I mean, I know it has to be vertical, so it's either up or down, but it has a magnitude of 1. And then what you're going to do is you're going to solve your internal forces. And just make sure I'm consistent with the notation that they use in here. Yeah, okay. So here, what you're doing is you're saying, I'm going to solve this truss. And these internal forces are F sub I, the internal force in member I. And then I'm going to go here, and I'm going to solve my internal forces. And I'm going to get lowercase f sub I. And fundamentally, my displacement, the equation that I get for virtual work, is this thing from the handbook, where delta L is PL over AE. And so for all of the members, you're multiplying Fi times lowercase fi times capital Fi, L over AE. And that will tell us our displacement in the upward direction, because I put that internal force upward, or I put that imaginary force upward. The beams, it works fundamentally the same way, but we do it with integration, which, again, just a joyous time for all. So for a beam subjected to some kind of loading, so here is some loading W, and I want to find the rotation at B. Again, what do we want? I want this particular quantity at this particular location. I could also find the displacement at some other point. So I could say, oh, here's point C, and we could do that with a unit force at C then. That's, sorry, unit force. Whatever. Again, it's important that you know what you're looking for. So we would create an additional structure. So if I want to find the rotation at B, I would inject a unit moment at B. Again, direction doesn't matter. It's whatever I assume it to be. It has to be a moment. So I could make it, say, counterclockwise with a magnitude of 1. For the vertical displacement at C, I would put a unit force. Upward, downward, doesn't matter. You make a choice. And so now what you're going to do is, with this structure, you're going to find the internal moment, m of x. Sorry, this one should be a capital M. Right? You cut the beam at some arbitrary position x and find moment as a function of x. For this rotation at B, we're going to find our internal moments, lowercase m of x. We're going to cut the beam at some position x and find the internal moment, lowercase m, because that is the virtual moment. It's not coming from a real load. Here, if we were doing this one, we would have two functions. M1 of x over here and M2 of x over here. Right? Because those moment functions will be definitively different. And so what we're doing now is, if I'm finding the rotation at B, this rotation at B, which by my assumption is counterclockwise, that is equal to the integration over the entire length of lowercase m of x times capital M of x over EI dx. If instead I'm looking for this vertical displacement at C, then what I'm doing is I'm saying that V sub C, and since I've put VC, since I put that unit force upward, V sub C is assumed upward. That is equal to the integration from A to C of lowercase m1 of x times capital M, or specifically m1 of x, divided by EI dx, plus the integral from C to B of lowercase m2 of x times capital M2 of x over EI dx, where in this particular circumstance, capital M1 and capital M2 are both identical and they're both equal to capital M of x. And that's all there is to it. It's just a matter of drawing free body diagrams, solving for these internal forces. So only 6 minutes over time. I think I should be celebrated for that. But anyway, are there any lingering questions, comments, concerns? Everybody's
None
going to
here.
knock this stuff out of the park and make me very proud.
Absolutely.
That's what I like to hear. All right. Well, with that, then I'm done. If you have further questions, you're more than welcome to contact me, and I will be happy to try to help. Otherwise, thank you very much for your time and attention. Do very well on this exam. I have confidence in all of you. Thanks.